Welcome to the final part of Astrophysics Revision. I am Will Carne.
And I am Connor Durkin. Now, things really start to hot up here, and this video deserves just a like and a favourite for that pun alone.
As we move from the big and the bigger to the really rather large.
And with the help from the WAHEY Productions Escort to the Exam, we will get you an A star if you, well, we try.
Yeah, and we strive to quench your impregnable thirst for star-related banter.
And moving on to supernovae.
We really love it.
The evolution of a star is related to its mass, and the Sun is relatively small, and so its fate is somewhat dull, as we've outlined before.
But larger stars are more likely to have a catastrophic and much more stirring end.
One example are supernovae.
Supernovae are objects which exhibit a rapid and enormous increase in absolute magnitude, and there are many types.
Main one you need to know is Type 1A supernovae. These occur due to an exploding white dwarf star which is part of a binary star system.
The white dwarf increases in mass as it attracts material from its companion.
Eventually the white dwarf reaches a size which allows fusion to start again, causing the star to explode.
This occurs when the star reaches its critical mass and produces a very consistent light curve as shown.
Look at that. Note that 0 is always placed under the peak.
Yeah. In fact, Type 1A supernovae are useful because they reach the same peak value of absolute magnitude, making them standard candles.
So the absolute magnitude is known, so the apparent magnitude can be measured, so the distance can be determined.
Another advantage of using a Type 1A supers is somewhat obvious, that they're bright.
This means that you can use them to measure distance to the furthest galaxies that we can see.
Now, recent measurements of this kind have led to the idea that the expansion of the universe may be accelerating and that controversial dark energy may be driving this expansion.
This means two things. We need you lot to go get physics degrees and study this stuff and work it all out, and worst of all, astrophysicists can no longer use Suvat equations.
Obviously, other supernovae do exist, and when the core of giant stars stop generating energy by fusion, gravitational collapse can take place.
The core may form a neutron star or a black hole, depending on its mass, and the gravitational energy release can cause the star's outer layer to heat up and die, or worse, expelled. That was expelled.
Well, just expelled for the Potterheads out there.
Miss Emma Watson.
Yeah, over to the WAHEY Production to Escort to the Exam to yabber on about neutron stars.
Yabba. When a giant star has exploded its outer layer, the core may be too massive to become a white dwarf, and further collapse can take place. A core with a mass of about twice that of the Sun will form a neutron star. It's believed to consist largely of neutrons, obviously, though some theories suggest it may have a crust made of atomic nuclei and electron fluid, with protons and neutrons making up the interior. Due to the complex nature of its structure, other properties are considered to be its defining features. They're believed to have the density of nuclear matter and to be relatively small, about 12 kilometres in diameter, or an Everest and a half. Due to the conservation of angular momentum, they tend to be spinning very rapidly, though they don't lose energy and slow down with time. They can be very powerful radio sources due to their extremely strong magnetic fields. This, combined with their spinning, produces pulsars, which behave like radio lighthouses, and produce the invention of dizzy dinosaurs. An example, though, of a pulsar can be found in the Crab Nebula. An example of dizzy dinosaurs can be found in the primary school playgrounds in 2004.
Black holes.
So basically, when the force on a core passes the first threshold, electrons are squeezed into the nuclei, piling up with the protons to form neutron stars and releasing plenty of neutrinos for conservation.
But if there is even more inward pressure, then the next critical point can be crossed.
So more massive cores can continue collapsing to form black holes, where the laws of physics become as useful as this diagram.
That diagram is the most useful thing I've ever seen in my entire life.
Oh, sarcasm.
The defining feature you should focus on is that the escape velocity is greater than the speed of light for a black hole.
Yes, and
the boundary at which the escape velocity is equal to the speed of light is called the event horizon.
Anything within the event horizon of a black hole cannot escape, not even light.
Apart from the odd hero in sci-fi films. Yeah.
Now, the radius of the event horizon is referred to as the Schwarzschild, or RS.
Schwarzschild radius.
And the equation is apparently easily obtained from Newtonian gravitational theory.
For a black hole with an escape velocity equal to the speed of light, c.
It gives RS as 2gm all over the speed of light squared.
Where g is the universal gravitational constant with 6.67 times 10 to the minus 11.
And big M is the mass of the black hole in kilograms.
From this, it is important to note that unlike a neutron star, the density of a black hole is not necessarily very large. It's believed that supermassive black holes, whose mass may be 7 million times the mass of the Sun, exist at the centre of most galaxies.
And the density of these black holes may be similar to that of water.
Ooh, lovely. So it could float. The radius of a black hole is proportional to its mass, which means that the volume is proportional to its mass cubed.
Now, you should know that the density is mass over volume, so the density of a black hole must be proportional to the inverse square of its mass.
So the more massive the black hole, the less dense it is.
Yeah, well, no, that is actually true. It is actually believed that a quasar is produced as a supermassive black hole at the centre of an active galaxy consumes nearby stars. But we'll come on to quasars later.
I'm a firing my quasar. On to the Doppler effect, or perhaps the best demonstrated...
Love it.
Big Bang Theory. As the source of sound of a sound wave approaches, the sound waves are bunched together, reducing the wavelength and so therefore increasing the frequency so it's higher pitched.
As the source goes away, the waves are stretched out, increasing the wavelength and so reducing the frequency so it's lower pitched. Love it. And the same thing happens with light.
But the size of the effect depends on the ratio of the speed of the object to the speed of the wave.
So it's less noticeable with light unless the source is moving very quickly.
As with sound, if the light source is moving away from the observer, then the wavelength is increased.
This is often referred to as redshift, as red is at the longer wavelength of the visible spectrum.
You may have heard of blue shift with things coming towards you, but we would just refer to that as a negative redshift.
Now, redshift is given this symbol Z and can be calculated with the following equation.
Z equals the emitted frequency minus the observed frequency over the emitted frequency, or the speed of the source over the speed of light.
But only when the velocity is much smaller than the speed of light, or it doesn't work.
Or for wavelength, the emitted wavelength minus the observed wavelength over the emitted wavelength will give minus Z, as the wavelength decreases if the source is approaching.
Yeah. It's blue shift, technically.
Blue
so
shift.
A typical application in cosmology is the study of eclipsing binary star systems, so two stars rotating about a common centre of mass.
In our line of sight, one star passes in front of the other, causing an eclipse.
Here is a simplified light curve from an eclipsing binary system.
Imagine one star is big and bright and the other is small and dim, or, as we like to call them, Brian and Dave.
As Dave goes in front of Brian, it blocks out a bit of Brian's brighter light, so there's a dip shown as the apparent magnitude scale increases going upwards, that light dims.
But as Dave goes behind Brian, you have a loss of Dave's light, which is dimmer anyway, so there's a dip, but it isn't as deep as the other one.
Yeah. Now, the key thing to take from this graph is the fact that the time period will be constant if their orbits are constant.
If you analyse the light from one star in more detail, then the shift in wavelength of one particular spectral line can be measured as the star follows its circular orbit.
The peak will occur when the star is going away from us at its maximum velocity, so when the two stars are next to each other.
The eclipses occur when a star is moving at right angles to our line of sight.
And then the wavelength is blue shifted to the max when it's moving towards you at its highest speed.
Again, from graphs like this, it is really easy to find the time period.
Now, you can use the graph to work out the redshift using the earlier formula for wavelength.
Looking at this using the Balmer series, you can see how the absorption line moves corresponding to the red-blue shift due to the star moving away and towards the observer, or you lovely people.
Yeah, we'll touch on this with quasars a little bit later. It's so exciting. We're building up the excitement now.
Dun 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 dun.
Observations of distant galaxies. Galaxies, not stars, focus. Observation of distant galaxies, just hammering that home, showed significant redshifts, and further analysis suggested that the further away the galaxy was, the greater the redshift.
The Doppler equation was used to calculate the recessive velocity of galaxies, leading to the development of Hubble's law.
The law deals with the relationship between recessive velocity, v, and distance, d, for galaxies, stating v equals h multiplied by d.
Where h is Hubble's constant, the currently accepted value for which is 65 km per second per megaparsec, although knowing astrophysicists, that would have changed by the time you've watched this.
Note, therefore, that the velocity is kilometres per second and the distance is megaparsecs.
A graph of velocity against distance can be used to determine an approximate value for Hubble's constant by working out the gradient of the line of best fit passing through the origin.
Now, all the data suggests that the universe is expanding and everything seems to be moving away from everything else.
And Hubble's law suggests that there was once a common starting point.
As the distance between the galaxies was zero at the start, the time since the beginning of the expansion, so the age of the universe can be found by dividing the distance to a galaxy by its recessional velocity.
This gives an age of the universe of approximately 15 billion years.
Ish. Or 5 minutes before the birth of Bruce Forsyth.
Haha! Old joke. As time is distance over speed, you're just rearranging the equation to get 1 over h.
H has got horrible units, but if you can compensate for that by putting your answer in years, so you should get that too.
You just did the intergalactic equivalent of counting the spots on a ladybird's back.
And to be honest, some astrophysicists think that it's about as accurate as a spot thing.
As the equation assumes that the expansion rate is constant, yet recent evidence suggests that the rate of expansion may be increasing.
Yes, and now over to the last time in astrophysics, and possibly ever, to the WAHEY Productions escort to the exam for the lowdown on dark energy.
At the end of the last century, astronomers measured the distance to several very distant Type 1a supernovae and measured the redshift of their host galaxies. They expected to find that the rate of expansion was slowing down and that the supernovae would appear brighter than suggested by the extent of their redshift and Hubble's law. What they actually found was that the supernovae were dimmer than expected, suggesting that the rate of expansion of the universe was increasing. Further measurements since then have supported this idea, and in order to explain this increasing expansion, some astronomers have used this controversial idea of dark energy. At the moment, there is no known mechanism for this expansion, or the dark energy that drives it. Some astronomers believe that it is linked to the cosmological constant introduced and then discarded by Einstein during work on that little-known phenomenon, gravity. Some believe it's due to negative vacuum pressure or the quantum field effect. Some believe that it's God just making a room to extend hell for the growing population of atheists, and Kyle, aged 12 from Essex, has drawn an illustration as valid as all the other theories. Thank you, Kyle. Your WAHEY gold badge is on its way. But the fact is that there is evidence for its existence, and that as no one knows what it is controversial.
So, the Big Bang Theory, which in a nutshell is that over the past 15 billion years or so, the universe has expanded from an extremely hot and dense point, and it's still expanding.
So physicists drew a graph of what they knew and just continued their line of best fit back to a singularity.
But there is evidence from the Hubble relationship and observations of redshift of distant galaxies, which we've already sort of touched on.
And even more evidence comes from the discovery of cosmological microwave background radiation.
This is a glow in all parts of the universe, the spectrum of which follows a blackbody radiation curve, with a peak in the microwave region.
This peak, if you're wondering, corresponds to a temperature of 2.7 Kelvin.
You can think of it as leftover heat from the Big Bang, the photons having been sort of stretched to longer wavelengths and lower energies.
Well, you could say that it is the radiation released when the universe cooled sufficiently for matter and radiation to decouple, with the combination of protons and electrons to form neutral atoms. Leftover heat.
Yeah. So even more evidence comes from the formation of nuclear matter.
The theory suggests that a very brief period of fusion occurred where the universe was very, very young, resulting in the production of helium from fusing hydrogen.
The universe then expanded and cooled rapidly for the creation of larger nuclei, resulting in a relative abundance of hydrogen and helium spread uniformly throughout the universe.
And a lack of larger elements, which is consistent with what you generally find now in the universe.
Now, some people find it hard to get their heads around the idea that the universe is expanding all over the shop.
A good way to think of it is like a balloon with dots drawn on it, where the dots represent galaxies. As the balloon is inflated, then they move away from each other in all directions.
Yeah. And finally, quasars. We promised, so here it is.
Quasars were first discovered as very powerful radio sources, and due to the poor resolving power of radio telescopes, it was very difficult to associate a quasar with its optical counterpart.
They seemed to produce a continuous spectrum that was nothing like a blackbody radiation curve, and instead of absorption lines, there were emission lines, of which never seen before elements.
Then someone pointed out it was just like a Balmer series for hydrogen, redshifted massively.
This means that they are really rather far away, billions of light years away, and using the inverse law for intensity, you can work out for yourselves quite how bright they really are.
Redshift measurements suggest that quasars are the most distant and most powerful observable objects in the night sky.
Yes, and using the inverse square law, calculations suggest that they can produce the same power output of several galaxies.
Variations in their output, however, suggest that they may only be the size of a solar system.
They appear in the centre of young, so distant galaxies, often obscuring their host galaxy because they're so darn bright.
And they are now believed to come from supermassive black holes at the centre of active galaxies.
Yes, and all the astrophysics on that is currently being updated every single day. And that is it. That's the whole series. That's the end of astrophysics.
Done.
We're finished.
It's over.
And that's the end for physics for your A-level. So have very good luck in your exams for 5A4 and 5A5.
Calm, friendly letters.
You'll be fine.
Maybe.
It'll all be good. Multiple choice, etc.
Etc, etc.
And that's it for us. Do come and look at all our other videos in the summer. We'll be very busy.
Very busy.
Next years. Oh, and recommend us to younger siblings.
Everyone.
And just generally. That's it. Advert over.
Right, we're going to
follow us on Twitter, tweet us, comment us, Facebook us, Fackybook, Pinterest us.
Pinterest?
I don't know what Pinterest is.
I have no idea what is Tinder. Oh no, not Tinder.
Tinder.
I don't need to.
No. Tinderbox. It's a really nice coffee shop in Islington.
That's not what I was thinking of.
Go to Tinderbox. I highly recommend it. Meet us there. I'll have a coffee.
We're slightly delirious. It's very hot in this room and it's been a good few hours.
Right. Thanks for listening.
Thank you
very
so much
good luck.
for listening.
One last time. Goodbye.
Goodbye.